All right, so thank you for joining my talk. This ICASSP presentation is about the paper explaining speaker and spoof embeddings via probing. So without further ado, I think we can just go ahead. So a little bit about our objective. So we know that audio deepfake spoofing attacks have posed a deep threat to the automatic speaker verification systems, where modern speaker verification systems often use embedding representations to train backend classifiers or to directly make decisions, answering the question that, such as who is this person. Meanwhile, we know that countermeasure systems, modern countermeasure systems, uh, if well trained, can answer the question that is this a real person? Hopefully helping the ASV system to make better this to prevent ASV system from being attacked by synthetic or converted voices. Countermeasure spoofing detect or modern spoofing detector also use embedding also generate embedding representations. So those embedding representations can answer their corresponding questions, can complete their corresponding task. But of course, they are completing the corresponding task within the setup, and it's more like a lab-like or simulated environment. But meanwhile, we know that there are still challenging conditions or even conditions that are unseen. And so parallel to making the system large scale or making the system, or piling more data, for example, we think that analyzing what information is captured or encoded and properly preserved in the ASV and countermeasure spoofing detector systems or their representations are necessary. So this is so to this study is to basically answer the question that what information do the embeddings capture. So we regard such explainability study will be helpful for the community to enhance the system against against the challenge, especially unseen challenge. There are a little bit about related work. So uh, so we're pretty the community has been pretty familiar with speaker embedding, which has been there for several years already. And the embeddings are usually obtained from the linear layer output, and it can naturally perform multiple tasks, such as capturing speaker identity or performing speaker related other tasks. And there are also previous works shows that speaker embed as shown at the right bottom of the figure. It is from ASRU 2019. It shows that ASV embeddings can capture multiple speaker-related multiple attributes, and it and via it is done via the study is done via some certain probing analysis on some downstream tasks, on some speaker and speech-related downstream tasks. Meanwhile, spoofing embeddings, or let's say the countermeasure embeddings, CM embeddings, they are rather less well known, or let's say less well explored. But of course, but modern countermeasure systems are also heavily rely on deep learning solutions. They heavily rely on deep neural networks, and they can also generate embeddings, which in our case, where we use assist, it is extracted from the last layer before the output linear layer, and it is as I said, less explored in terms of information has been encoded. So we perform probing analysis under spoofing context for both type of embeddings. Probing analysis has been widely used in the field for explainability, and by saying probing analysis here, we're talking about using linear classifier to predict non-estimated regressive labels with different objectives, of course, from hidden using the hidden representations. In this case, is the embeddings. We use linear classifier to perform such analysis. So then let's go to the main methodology. So speaking of the probing analysis, basically we are training a simple two-layer neural net. This is our setup to predict specific traits or specific attributes to extract from the extracted ASV and CM embeddings, as shown in the right-hand figure. We see that the input from the bottom is actually ASV or CM embeddings, and we feed it to a neural network, and the output, which is shown at the upper side, is actually it is actually the speaker, the speech or speaker related certain one type of attributes. So the hypothesis is that if the performance is high or good on a certain trait or attributes, it indicates that the trait has been, well captured or well preserved in the embedding. So in terms of that, of course, then one natural question is that what kind of attributes or traits that we would like to explore. So so we are using ASVspoof 2019 LA, and in such case, after some exploration, we have divided the attributes into two main categories. So the first category as shown here is the meta attributes, which is the one from the basic statistics or the metadata of the dataset. They're directly available in the dataset, such as speaker information, uh, like speaker ID, gender, age, and the accent of the speaker, no matter they are good, no matter they are real or fake, and spoofing type IDs, such as spoofing attack ID and the type of attacks, whether it can be text to speech or it can be voice conversion attacks. So we encode for each attribute, we encode that into the one hot label, and those one hot labels are served as the output, as the label for training, and we use cross entropy loss to train the network, treating this as a classification task. Then the second category is about the physical attributes. So this, instead of directly available from the metadata, this should be estimated in a per audio manner from the audio. So we extracted. So we use certain toolkits to for each utterance, for each audio piece, to estimate multiple attributes as scalar value labels, such as f0, speaking rate, signal to noise ratio, and duration. So if you are interested in about the toolkits we use to estimate them, please refer to the paper. And so the input, of course, is still either ASV embedding or CM embedding, depends on which one you want to probe. And the training is done via mean squared error loss function, and we treat it as a regression task, of course. Then that concludes the introduction of our probing framework. So let's talk a little bit about the experimental setup. So the data set we use is, of course, as I said, is spoof 90LA. So it's derived from VTTK, plus a lot of various spoofing attacks based on text to speech or voice conversion. That's what we call the type of attack. And we here, because of our task, we only use the evaluation set and split it into via a 9-10 portion for training and evaluation with completely overlapped speaker labels. We did this, of course, because we are predicting speaker ID, so we need to make we need to make the test set inset in the sense of covering all the speakers. The backbone models were for SV is ECAP-ITDNN, the still somehow at the state-of-the-art level speaker embeddings, and for countermeasure is one of the state-of-the-art level model again called assist. So then speaking about the evaluation matrix, so for classification types, of course, classification accuracy, and for regression tasks, we here use a matrix called R-square value. It is actually a statistical matrix to quantify how much variance has been captured. It is a matrix to evaluate how it can be interpreted as how well the model fits the data and how much variance in target variable that can be explained by the model. In such case, similar to accuracy, the higher the R-square value, the better, which means that the corresponding attributes can be properly correlated and explained by the trained probing network. So in terms of the results, so we see that at the right figure for each attribute, there are blue and orange bar. Blue is for ASV embeddings, and orange bar is for CM embeddings. Of course, higher bar means higher accuracy for each attributes. So we can see that ASV embeddings predicts, speaker ID pretty well as expected, and of course gender and spoofing attack information. Meanwhile, countermeasure embeddings are moderately good at gender and the spoofing attack information. So there's meanwhile, if we're looking at the results for each attribute, we see some interesting things. So speaking of the speaker ID, of course, this is kind of expected. ASV does well. CM is not doing well. So basically, that means that CM embeddings are it kind of discarded the identity of the speaker. And for gender, the ASV both embeddings are doing pretty good, but CM embedding is not doing as good as ASV embeddings. We'll see. We'll relate this a little bit later. And for age and accent, both are not doing well. But of course, this may be due to the VCTK, which is the source from that used to create ASVspoof 19. That VCTK is not varying a lot in terms of these attributes in the original audio data. And when we're looking at the attacking ID information, we see that surprisingly, ASV embeddings also capture spoofing information. But in our context, we think that meanwhile, this may count as part of speaker information. So this kind of like echoes some earlier research on session variabilities. So basically, this result means that under certain condition, ASV has certain potential to perform spoofing attack. It's just that it needs some future work to do. So by itself. So moving on to the physical one, we can see that both again the blue bars is ASV, orange bars is CM, and the higher the R-square value, it means that those embeddings capture corresponding attributes or trace corresponding information better. So both embeddings encoder can indicate F0, speaking rate, and duration, not SNR. So obviously background noise should be, background noise is normally regarded as the one that interrupts the decision for both ASV and the countermeasure task as expected. So for F0, the spoofing detector may preserve F0 as expected for detecting artifacts. Meanwhile, we know ASV should regard F0 as part of the speaker identity, speaker information, and but in terms of speaking rate and duration, these CM embeddings also does moderately good on it. So for speaking rate, it may be because that in order to detect speech synthesis methods, which may introduce slight mismatch in speaking rate, it needs to preserve such information for its judgment. But meanwhile, for duration, this is kind of a little bit unexpected. So maybe starting any impedance may contribute to this unexpectedly moderately good performance. So there are some main takeaways from the results. So we can see that surprisingly, the two embeddings share a lot of common information as from the performance. You can see that in a lot of attributes that both embeddings are doing pretty well. And the key difference is about speaker information. So we see that ASV embeddings preserve speaker-related information, and CM does not preserve that much, with a little bit unexpected finding regarding gender and duration. So we think that ASV can be effective for moderate spoofing detection, but CM can counter the contrary. So regarding the unexpected findings, we conducted 2 ablation studies regarding the gender and duration. So in terms of gender, we extracted 2 features from the encoder side and embedding side, the earlier side and the later side of the spoofing embeddings. We can see that the gender has been somehow normalized by the deeper layers of CM detectors, which means that countermeasure tries to be gender invariant. Meanwhile, for speed perturbation, for the duration of speaking rate issue, we perform speed perturbation, which we found that the countermeasure detector seems sensitive to the change in duration of speaking rate. This indicates the reliance of robust spoof detection systems on pacing or duration. So in summary, we propose a probing-based analysis. We have conducted probing-based analysis to analyze what information has been captured by ASV and CM embedding representations from modern systems. Even if the primary task is different, ASV and countermeasure embeddings include decent amount of information in common. But meanwhile, we can see that the modern neural-based countermeasure discard a lot of speaker-related meta information while preserving spoofing-related speaking and speech characteristic for detection robustness. And last but not least, future work may focus on leveraging the captured information and identifying the proper handling method for the missing discarded ones for better performance. And that concludes my introduction of this study. And thank you for listening.